or good afternoon.
Good afternoon.
So we will talk a little bit about two topics today. Stress transfer in volcanoes, and the scaling and analog experiments maybe in the second part. Stress transfer, maybe you have talked already about stress transfer in seismology. Stress interaction, a little bit of this. Yeah, so we will touch a couple of topics to show what observations you can have in volcanoes, and then we will touch it again in the last day, because we will do remote triggering of volcanoes by earthquakes, by these kind of things, and so we will touch again this topic, how a large earthquake can trigger a volcanic eruption. I will go through an example which I think is very instructive, and it is, we are again in Iceland. This is the north of Iceland. This is the, we didn't talk about this yet, right? No, because it was in the end of the slides that you got last time, but I didn't go that far. So actually you will find a superposition in the slides of last time, and this time it doesn't matter. Okay, so this is North Iceland, and this is an offset of the spreading center. Okay, it's often offset, so you have like a segment of the mid-ocean region, then another segment, and then you have an offset. We had, however, already described that these offsets in Iceland are a bit weird. They are not just one individual fault that slips, but it's divided over many faults. One possible reason for this is that it is younger than most mid-ocean ridges segments. And one other possible reason is that it is continental crust. It's like, we talked about that. It's like a piece of continental crust that was left over during the breakage. And so it's more thicker. And it is also, maybe the rheology is complicated because it's also heavily intruded with a lot of basalts. And so it has a more complicated structure. Anyway, what is in this figure is striking is the, so in orange, all these dots is the seismicity from the year 1995 or 6. That was the year when network was installed in this area, okay? To, actually the paper goes 2013, so maybe until 2012. Let's see, these are the earthquakes that occurred in around 20 years, a bit less in the area, while the stars are the historical earthquakes. And one can see, first of all, that there were 9 earthquakes of magnitude between 6 and 7 in this area since the year 1755. So this was the year when they started to actually have very good records of people living in this area and writing letters, documenting things. So from the descriptions in these letters of what was occurring, they could estimate a magnitude for these earthquakes. And they are, so what one can observe, basically, so of course the locations are not very good of those earthquakes because we don't know. So they are based on the effects, on the analysis of the effects of the earthquakes. And of course the locations can be bad, and also especially because we are offshore here, partly. So we don't know, you know, it's kind of known that the earthquake is onshore or offshore from the effects, but where offshore is hard to say, okay? So you don't have to take it very precisely. Still, if you observe the distribution of these stars and these earthquakes, and the earthquakes today, one can see that there is a difference. Like there are like 3, 4, like a few of them, like this one, and these two, that are located in areas that now are very active. But there are these 3, and these, and potentially this is actually probably one that has a very uncertain location. So let's consider this one and these three. They are in areas that are actually not very active at all today. So already this figure is why. Why would you have something like this? Like sometimes you may find such a case, you know, when analyzing the catalog of a specific country that you're working on or so, you find that you have maybe 10 years, 20 years, depends on the country, seismicity catalogs. And then you have historical data, and when you compare them, somehow they agree and somehow they don't agree. And then you have to consider why so. What can be the reason of a mismatch? Is it like the historical catalog wrong? There may be several reasons. So I think this case is instructive for some thinking. Anyway, one other information is to ask also local people. And if you ask local people, like we have colleagues in this area who have parents and grandparents, and if you ask local people, they said, oh, actually it's true, it's a very weird area because before the year 1975, there were a lot of earthquakes, also here and here in this region. This is what they say. It's hard to actually document this stuff if you don't have enough data, because there were a few stations and I think they are working now at a better catalog for the 20th century. But if you don't have any data, it's hard to say. Anyway, they were saying people building bridges, people building housing, they were saying, actually in these towns that you have there, you felt very, very continuously shaking from earthquakes. And then everything switched off. You remember what happened in North Iceland in the year 1976? There was these dikes, you know, you had these dikes and the plate splitting episode. After that, or during that, because it was many dikes, you remember they were, the biggest came first and then you had several smaller ones over 10 years' time. They said that they were calling this episode Krapla fires. This is the name that people gave it to this because they were seeing the eruption. So Krapla is the name of the volcano, and fires. During the Krapla fires, seismicity for some reason became very quiet. And then you can read it. So we read, this is actually work of one of my ex-postdoc. We were reading this a paper that described the seismicity in the 18th and 19th century and 20th century, and then there was written just this sentence, like anecdotal accounts from people explained that actually seismicity was very, very intense before the Krapla fires, and then these dikes acted as a cooling for the earthquakes. How can this occur? And then if you have learned something about stress transfer, what would you try to do to actually prove or disprove that the dikes had an effect on the seismicity? What would you try?
I think the dikes are releasing the stress. That's why.
Sorry?
When the dikes are chemicals, they are releasing the stress.
They are releasing extensional stress. Mm-hmm. Yeah. And what about stress on faults? That is, surely it's true. So when they came, they released extensional stress on, because the dike was here. This is Krapla volcano, and the dikes went all the way here. Actually, this earthquake was probably triggered by the first dike, almost certainly, because it came exactly 2 or 3 weeks after the very big first dike went all the way to here. And what about this area? Why should a dike affect this? And why, first question, and second, how can I prove whether a dike is affecting this area or not in terms of stress? It's it's not a difficult question, it's just to start the conversation. So what have you seen in terms of stress transfer? What is the method that people use to check whether there is any stress transfer from a fault to another fault, whether a fault triggered another fault or not? Have you seen this? Have you?
Coulomb failure function.
Yes, yes.
And
Yeah, so people use this Coulomb failure function. What is the Coulomb failure function? It's basically a complication of the very simple experiment that Galileo was doing, with the inclined plane. He was putting a mass, and then he was seeing how, friction was halting this mass, and then creating a velocity, for the mass rolling down, and then you had to. Basically, you had the inclined plane with an angle, and then you had a mass, and then in order to see whether friction was enough to stop the mass, you had to project the weight of the mass on the plane and tangential and normal, right? Coulomb failure stress is the same. It's just with stress rather than just with tangential force and normal force. So you use normal stress and shear stress, okay? So basically you consider a lot of planes. We will talk about what planes later. And then what you have to do is to consider I have a helper.
Yeah.
So still didn't help.
So it's a backstage one.
Yeah, exactly. Maybe this time I remember to record everything with the helper. So a little helper.
I remember my early professor, so I was his only student, so he would call me.
Yeah.
So sometimes he may bring his kids, 2 kids. So they would play here and we would study here.
Yeah.
And sometimes he may run after them to give them back. And then it was fun.
Yeah, it's fun.
Yeah.
It's true. I had a class when I had him like this.
That's nice.
No, he's too big. So, little helper, you can help by reminding me to push all the buttons to record the class, because last week I made a disaster. So if you see that I'm changing, that at the end, at the beginning, I have to push the buttons, okay?
Okay.
Cool. So what I was thinking, Coulomb stress. So basically, what can we do here now? We have a dike. Most studies of Coulomb stress, they are based on the stress change induced by a fault. So basically, what do? You take one of those stress models. Do you know how they work? Actually, I have a good student with a good code. I will see if I can run it to show you better, but maybe next days. What you do, you basically you use dislocation theory, right? So you use elastic dislocations. Dislocations are solutions that were found actually originally really for geophysics, but they work across many scales. They work from the very microscopic scale, in crystals, to show these defects of crystals, and then what stress is like a mismatch, like a misorganization of the atoms. So what stress will it cause in the overall volume of the crystal? It's the same on Earth. You have analytical solutions for this. The most famous one are called, is basically square dislocations. Then there are triangular dislocations that are more modern and actually more useful. I will show you that later. So these square dislocations work for everything. They work if you can put a shear on the dislocation. So basically you have like a plane. On this plane you have a shear like this or like this. It can be inclined, it can be twisted as you prefer. You can add several of them, or it can be opening. Okay. So in order to see what stress an earthquake causes, you put a shear dislocation where the earthquake fault is. You apply a displacement, because these dislocations generally work with a constant displacement along the entire fault. So you have a fault, and everywhere is the same displacement. It's just one individual one like this. You can compose many of them. In this way, you can also vary the slip on the fault surface if you like, but then you need to have a more complicated model with many dislocations. Okay, you can do the same with a dike. So you put the dislocation plane where the dike is and you open it. And then you calculate the stress. This is by analytical solutions. It's, it's already coded. It's not really very difficult. And then what do you do to calculate the Coulomb stress? You calculate the normal and the shear stress, and you, exactly as in the inclined plane, you say shear stress, when is it bigger than the friction times the normal stress, then I will have a higher likelihood to have a slip. So I will favor earthquakes. If the friction times the normal stress is much larger than shear stress change, we are talking all about changes induced by a fault, then I will actually tend to switch earthquakes off. It's like a probability, it's like a stochastic process, so it's like an increased probability of having earthquakes. People talk about this like increased probability or decreased probability, or they talk also about clock advance and clock delay, because basically what you can do is actually anticipate an earthquake because you provide a little bit more of shear stress, just what is needed to actually trigger the earthquake, but there was already in the fault stored some stress. You just advance the clock, internal clock of that fault, or you can delay and then you postpone an earthquake by this. You remember the case where the dike hit the fault and then basically it advanced everything which was here in this region and it switched off everything which was here in this region because it wanted a motion that was favorable here and unfavorable in this area. Okay, so basically what happens, now I made this very long preamble, and this is a figure of this Coulomb stress. Okay, so it's a shear stress minus the friction times the normal stress. Okay, in order to calculate this, you always have a choice on whether you want your planes for faults to be every possible orientation, and then they are called optimally oriented, because basically you choose the orientation that has the largest shear stress minus F sigma n, because this is what, if you have faults in all directions, the one that is going to slip first is the one that has the biggest change, maybe, because actually you never know what stress was on the faults before. This is actually the most tricky point of all this procedure, is that you have not much information on the pre-stress. Generally you don't know. The only thing you can assess is the change. And this is a big limit, so consider this in these studies. Anyway, the dike is this. In this figure, the dike is this thing that was basically modeled just considering, I told you that people went to the field and measured the extension on the rift just by line. So actually there is a procedure even there to decide how big the dike could be, but more or less. So this is the dike. And then you have areas that are red and areas that are blue. Okay, so in this case it's not optimally oriented faults, but it's fault oriented as this fault here, because actually the whole analysis was on this fault here, because this fault here had this very weird observation, that part of the fault is very seismically active with historical earthquakes, and part of the fault has almost nothing with a lot of historical earthquakes. So let's focus on that fault. That is really a proper fault. And actually it turns out that if you do this Coulomb stress on this fault, you have a weird figure by which actually it's true that the easternmost part becomes real blue and the westernmost part is more red. So what does it mean, red and blue? Red is like you have a lot of shear stress in comparison to how much compression you cause, and when it is blue actually you have much more compression than shear stress change. So you are going to lock the fault. In the other case you are going to unlock it. Okay, so let's go first to have a look at how exactly this, before I do this, let's have a look at this. So this is actually the fault, and in this figure you can see, so this figure shows what happens to the Coulomb stress calculation if you rotate the fault just by a little bit. So you have a lot of uncertainties when you have these calculations. First of all, you can assign an orientation to the fault, but a fault is never really planar. A fault has a lot of actually wiggles. So what is the uncertainty in this kind of model? If you have some patches of the fault that are actually like this and some patches that are like this. And you see that it changes a bit, you know, you see from the figure that it does change a bit. And then actually in the paper I have the two more figures that I didn't put here, which show, I think I didn't put, maybe actually I'll open that later. They show, let's open it because I think it's instructive. Ah, it's actually this, so it's easy to access. Here. Okay, so this is the fault, this is the figure. Actually combined several of these in the figure. Okay, the first column. So this is for the fault exactly oriented like the average strike, here, here, and here. And this is divided by normal stress, shear stress, and total Coulomb stress. Normal stress, shear stress, total Coulomb stress for something 10 degrees like this. Normal stress, shear stress, and total Coulomb stress for something like this. What does this show? First of all, it shows that it does change a bit if you change orientation, so you have to actually consider that not all patches will necessarily respond in the same homogeneous way. You will have some variability. But also, you can see from this particular figure, but the others are similar, is that the shear stress change, and now I have to go. The shear stress change, if you look at the colors, is actually very small. It's not very big, while the normal stress change is actually really big. So this is different from a dike and a fault. Generally, faults really induce a lot of shear stress, but they don't induce at all much compression or decompression. They do a bit, because you know that, for example, a strike slip fault always creates a lake and a bulge on the two sides. So there is actually some compression and decompression, and you create this kind of thing. But a dike much more than that, because it really, you include magma, and the magma pushes the side of the dike apart. So actually a lot of the effects of this Coulomb stress was really due to compression on one hand and extension on the other hand. And shear stress was not much changed. So this effectively, according to this paper and this study, was the reason why seismicity got really blocked in the easternmost part of the fault. But it's not going to be an eternal thing, it's only a clock delay. Because, why? Because tectonics, slowly, will go and compensate. And this is about the next slide. Okay, let's have a look at this. This is the equation that you get if you have a step change in Coulomb stress. So basically what this equation tells you is that this is the local seismicity rate, which will be equal to the background seismicity rate, so the seismicity rate you had before, times this function where this is the Coulomb stress amount that you have. This is a normal stress, A sigma. Sigma is normal stress, A is like a parameter for the actual fault you have. You need to estimate it from your model. And then here you have time, and here you have stressing rate, which is the background stressing rate. So what is important? You have not many parameters. A sigma is like together, it always is together, and it is I measure how that particular rock responds to these processes. So it's like a parameter that relates to rock. And then you have time, and then you have stressing rate, so how much tectonics is pushing or pulling, like shearing. And then you have your actual Coulomb stress change. Okay, so if it is positive, Coulomb stress change, then you create basically a big jump in the seismicity, but this jump in the seismicity will be very quick. So it will go up a lot, but basically how much this Coulomb stress change is big will determine how big the peak is, but not so much the time of recovery. So basically what happens, you have your seismicity rate here is normalized at 1 before, you have a step change, and then you create this very big jump. You saw it already from other models, I think. Then everything, you create a lot of aftershocks, and after some time, that depends on this parameter A sigma, it may be weeks, it may be months, it may be years, it drops to values that were like before. But what happens if the Coulomb stress change is actually in the opposite direction, when you lock the fault? Then it happens that your seismicity rate goes down. It cannot go to 0. You just, because it's always a seismicity rate R big R over R. So it can go to a very small number, but it's not 0. So basically you abate the seismicity that you have before, but you, let's say, if your stations were powerful enough, you would still detect the tiny ones. You may see 0 earthquakes, but it doesn't mean that you have 0, 0, 0. Yeah. And then you cannot, like in this case, go up and up. So you cannot go down and down, because less than 0 you cannot have, right? And so you go long. Because actually the integral, the integral, the integral below the red curve needs to be the same as the integral below, like here. So this here is the same as this area if you calculate the integral. The reason why it looks different is that actually this peak is really steep, and you have a lot of space actually because it goes really, really high. And therefore, you need to go really long to compensate for the same thing. So basically, what happens? So if you have a locking, you go into seismic silence, and then you need to wait for tectonics to compensate what was taken out, or locked. You need the shear stress to grow and grow to compensate for this locking. And then you need to wait, because this is only tectonics going to provide. You need to wait for time, and it can be many years. And then at some point, it's interesting, at some point the seismicity rate will start to recover. Actually, it's not really linear, but almost near linear recovery. And then you will be here. So this is why stress shadows can last for a very long time, like in the dike in Japan. The last time I looked was 2014. There was nothing at all in an area that was really active. I don't know now. One can look and see. What we did in this particular case, what you can do, you can also go to the, so this is the seismicity rate, but you can also go to the integral, which is cumulative seismicity. Why would you want to go to cumulative seismicity rather than seismicity rate? Because always when you have a derivative, it's very oscillating, and when you have an integral, you basically compensate. You smoothen the function by integrating always, right? So if you go, you are more likely to see things in data if you create the cumulatives. So it depends on what, but in general it's a good trick. So what would I expect? I would expect to see this. before the earthquake, like a constant seismicity rate, and then before the dike, and then the dike abates the seismicity rate, so I would expect to see almost nothing. And then I would expect to wait for many years and see a recovery phase, which is this phase here, until I get to another seismicity rate that is like the previous ones, just later. This is the clock delay. One thing that I forgot to tell you is that in this particular model, it's tricky to check because the dikes occurred between 1975 and 1984, and the catalog started 1995. Okay, so you don't even have the time of when things happened. You cannot really check, right? So the only thing you can check is that you have like later, you have the data from later. So basically you can plot, you can divide your fault into some segments, and then you can calculate the seismicity rate over the many years. So if you look at this particular box here, you have something like this. If you look at this particular box here, you have something like this. Of course, the earthquakes become less and less, and so also the cumulative is a bit oscillating. Then if you consider this one, you see something like this, and then like this. If you consider this one, you see something like this, and then like this. And this one has only 30 earthquakes, so it's not really very precise or easy, but you see something like this. So actually, you may, if you have good catalogs, you may be able to see this. Like you have a very strong stress shadow. You can plot your cumulative seismicity if you are lucky and you have the catalog is good. Also from before, then you actually have a seismicity rate, then you actually go flat, and then you see it recovering again. In this case, you cannot see the phase when it went flat because it's earlier. You at least here it's proposed that you can actually see the phase when it's recovering. And now, so what is confirming is that people now say that in this area, yeah, it's starting again after so many years. People confirm this is just a feeling from people living in the area, but you can also see it from the seismicity. So actually it would be cool, I think, to check in the Japanese dike whether this is occurring slowly there again in the area to the south, west of the dike. Yeah. Do you have any questions on this? Maybe I'll ask you questions to check. Okay, I'll ask you a question. If you consider a fault, okay, here on the particular, okay, let's go to the map. No, I forgot to say something. Actually, one very interesting observation is that what changed also was the B value in the two phases. If you go before the king and after the king, before B value was low and after the B value was higher. So this may be consistent with the idea that when it's locked, it's pushed, very compressed, and then you have lower likelihood to have tiny earthquakes because you are so compressed that this doesn't occur so much. But then later, when the tectonic stress compensates, then you go back to the usual statistics. So my question is, very rarely, actually very rarely, quite rarely, suppose that this model really explains the observations in this area. Very rarely you have such a clear picture. So actually, there are very few figures in earthquake-earthquake interaction that look as good as this. Okay, it's a paper by me, but it's really true. It's not our merit. It's just that so if you compare, let's say, see, this is a complicated question, so I'm going to help you. What do you think are the differences in terms of okay, what are the differences? If you calculate the Coulomb stress in earthquake areas, so like in due to faults, due to earthquakes, and Coulomb stress due to dikes. Why? So I tell you, it works better with dikes. Why does it work better with dikes? What is the difference between a dike and a fault in generating a stress in the outside? Let's put like many arguments there, if you, whatever, you know. It's like a discussion to learn. It's not like to give the correct answer. What do you think is the difference between a dike and a fault? First of all, look at the dike and at the fault, how they are made, and also what also can be the difference in the region. So there are probably several reasons why it works better, but yeah, just maybe you have some ideas. I don't know. Like one possible idea is I anticipated before that faults are not really planar structures. So is this a potential difference with the dikes? It's not that dikes are really entirely planar, but they are much smoother structures. So they have some topography, let's say so. But faults are much more heterogeneous in terms of their topography. So faults are really they may be very complicated. They may be smooth if they are very old faults that have a lot of cumulative slip, but in general they have a topography and they have a lot of branches, and these branches are not necessarily linked and not necessarily parallel to each other. This is also true for dikes, because we saw that also dikes can be very segmented, but still they are much smoother, and the opening is much smoother. Like if you go and analyze the slip distribution on a fault, is often very irregular. You have patches with very high slip and patches with almost no slip, because you have asperities that block slip, and you have, it's very heterogeneous. And probably even the heterogeneity, you can't even see it very well from models or from inversions, because you need to apply some smoothing artificially when you invert for the slip distribution on a fault, because otherwise you don't know whether you are actually modeling your data or whether you are modeling noise. Right. But the dikes, if you go to the field, they look much smoother. Actually, they are really smooth structures. This helps when calculating Coulomb stress, because you have less variability, when you have a fault and the actual fault is all fragmented like this, and you calculate the Coulomb stress, it's going to be a very regular thing, and it's very difficult to. This is why also faults have a lot of seismicity on the fault plane. You can have an earthquake and then you have a lot of seismicity on the fault plane. This is really due also to this irregularity. Well, dikes are really smooth, and actually you have seismicity on the dike plane, but it's actually probably a little bit off the dike plane. It's due to so this is one reason. Another reason, maybe the tectonics is more clear. Like here you have like a spreading segment with a dike, and then you have a very well developed fault. So it's much easier to actually calculate the Coulomb stress, because you don't have so much arbitrary choices to make. You have the fault there, you have the dike here, the dike is this big, it has this opening and then you see the effect. Like for example, the Japanese dike would be even easier than this one to do, because you have a very clear geometry, smooth geometry, and also you have here in particular was a lucky case, but also the other Japanese case would be lucky because you have very high seismicity rates, and then it's easier to see a change when you have a change, negative change, if you have a very high seismicity rate to start with, because you really see it. If you have 0 to start with, how are you going to visualize a 0? You know, like a bigger 0. It's very, very difficult. So you need to have a starting situation where you have a lot of seismicity to actually see the stress shadow. Otherwise, it's very unlikely to be seen. Yeah. Well, maybe by discussing later, we will see better the implication of all this. Okay, just to show you a little bit better, this is the very best data that you can actually get from the earthquakes below the dike. Like a lady from Cambridge sent me these papers, and I wanted to show to you. Like this is maybe a very special case, I don't know. The dike was actually all above, we saw this, and the seismicity was all below. Very few earthquakes here, most of them actually were here. They say it is the brittle ductile transition in Iceland. So why would you have a lot of earthquakes occurring at the brittle ductile transition when you have a dike? Why exactly there and not in the rest?
This is during the time intrusion.
So basically you consider what tectonics do we have, so we have extension. And then you have an upper crust, let's say 6 kilometers, that is brittle. And then below is ductile. What happens in the ductile region when you are extending over, I don't know, 200-300 years or even 1,000 years? What happens? You stretch the brittle part, but you don't have any possibility to actually release that stretch. So it's accumulating. It's accumulating. It's not breaking, it's accumulating. And what about the rest? In the ductile region, you have enough heat to actually release that stress. So actually, basically, all the stress is in the brittle part, the stress accumulation. And in the ductile part, you don't have so much stress accumulation. Then you have a dike. The dike fills exactly the gap that would have been created by extension if that would have been, it basically fills the column created by extension. And what about below there? Suddenly you have a lot of stress. And the stress, why do you have a lot of stress suddenly? Because basically you wanted to stretch and stretch here and you couldn't. Okay? Here below, you are actually extending. And you create something like this. And then this is very quiet, there is no stress here, and it was opened by a little bit. And above, you have this that suddenly opens. And then actually, here you are creating a stress. In the time you open, because you have this rheology transition. And this is probably, it's true, so this is the reason why a lot of earthquakes occurred there, because basically this process of filling up this column from just 6 kilometers above or 7 or whatever it is, created just a lot of stress exactly there, at the bottom tip of the dike, which coincided with this transition. It makes sense. Questions? Let's have a look. So basically they look like this, they are really thin around the dike. You see, this is already exaggerated opening, 50 to 1, they plotted it. So you can imagine how thin it is, and the graben faulting above there. And then most earthquakes were actually here. This is during the propagation, a lot of earthquakes. During the eruption, some earthquakes. And after the eruption ended, just very few earthquakes. Let's have a look at the pattern So the pattern is really like, you see, one can even see the shape of the dike like this, which is the upper tip there, where it stopped. You can even see the curvature, and then you see all these patterns that basically show some, this you can only see, this is really beautiful, and you can only see it if you relocate the earthquakes very precisely by relocation methods to check, you know, you don't see it, generally you see just a big cloud. If the data are good, and if you use like a dedicated software to find, sometimes basically you find families of earthquakes, so there are different procedures to relocate earthquakes. It's not my topic, so I will not develop so much on this, but there are some that are based on similarity of waveforms, which then allow you to get a precise relative location between a family. You know, you have a lot of earthquakes that have very similar waveforms. It means that they need to be from a very close by location, and also the fault plane solution needs to be similar. Otherwise, you would have a different waveform. Either path, so both path and fault plane solution need to be similar for an earthquake to look similar. So if you have a lot of these that are similar, then you can actually use this similarity to cross-correlate the waveforms and get really very precise changes or differences in arrival times, or you know, at the different stations, and then you can figure a very precise relocation. It's a relative, because you need to, they are all well relocated with respect to each other, but actually the full crowd may move a little bit, because you, so this is one type. What they use in Cambridge is something different. It's based on back projecting the rays after, I don't know. It's a different procedure. But there are several earthquake relocation softwares that can be used to actually investigate the fine structure of the seismicity, and you can identify these very fine details. The color is different for plane solutions. So for some reasons, some earthquakes here, this is also interesting. So most earthquakes are green. You see, most of them are green rather than red. They plot in green left lateral earthquakes that are supposed to occur in this region, while there are less here that are supposed to be red. They go into a deep discussion of why the case is. So what is certain is that the dike was at a slight angle with the regional extension. It was not perpendicular to the extension. So probably the topography distribution, we discussed that also topography commands where a dike will go, you know, the trajectory. So probably the topography load and the tectonics played in a way. So I mean, there is a debate here that the dike anyway had a given orientation, but then the stress was slightly at an angle, or we don't know actually. We don't know why the dike was misoriented with the regional spreading. You see, regional spreading here is slightly, is not really perpendicular to the dike. It's just 10 degrees off. You know, this would have been perpendicular, and this was the dike. And basically, maybe this has generated the fact that most earthquakes were just on one side. You actually remember also for the Miyake-jima dike, it was, seismicity was actually on one side rather than on the other side. So there may be different reasons, but anyway. Another weird observation is that actually, if you look at the fault plane solutions, instead of being like this, which is what they are supposed to be, they were like this, very narrow along the dike. What they say in the paper is that they think the reason was a very high pore pressure that basically made the effective friction very low, very low. And this can change the orientation of the fault with respect to the stress if you have a very low effective friction. So they give this explanation. I don't think it's necessarily the only explanation. There may be other explanations, but so basically, what are these things? These are like really real observations that are very new, and they are not yet fully explained. So why are they at the bottom? Okay, maybe because it's this transition, and then you have the whole release and everything. But actually, this is not necessarily the case for other dikes. Like in Ethiopia, they didn't have this pattern just at the bottom. So, and there was probably the same process. So why do you have it in one case and not in the other case? So actually, there must be more to it. Another is, why do you have all that very fine structures? Another is, why do you have most left lateral and not right lateral? And then another one is, why they are like this, default plane solutions rather than like this. And these are still open, and maybe they will be clarified in the future or maybe not. But it's good to read about this, because you may find, if you look at, I don't know, in your later in your PhD into not necessarily volcano, but also geothermal earthquakes, or earthquakes in geothermal areas, or earthquakes in areas where you have a lot of fluids, you will find that the pattern of the earthquakes are very similar to volcano earthquakes, very similar, because you have this component of a lot of fluids playing a big part, and they will affect stress, and they will affect the ways earthquakes occur. So it's good to have seen them once. So this is another figure of this propagation velocity. We talked about it a bit. So we saw that the dike, first of all, here you see somehow that it went, I'm not sure why this is the case, but anyway, it looks like it went into this direction and then it stopped. But then it decided to go actually in this direction. There are a lot of dikes also in the Mandararo case that did this, like they tried to go into two directions, but then one direction died soon after, and then they went into the other direction. This occurs quite often, and the reason may be that actually really it's easier. So you basically try to start in all directions, but then stress really takes the dikes into one particular direction. Then there was like an accelerating phase, decelerating, accelerating, decelerating, accelerating, decelerating, and again here, and then again here. And then seismicity does, so you have areas where you don't have anything anymore, but you start to have actually kind of insisting seismicity there, and then you have areas where you don't have anymore. You certainly have this band, and then you have like a big hole. So there are a lot of things here that are hard to explain. This is actually very complicated. So I'm going to show you another one, which is from the Mandararo sequence in one of these papers by Manalo. So here you see many things. You see that you have this band. Maybe it started also in one direction, but it's very tiny, if any. It definitely went into this direction. Then you can see actually that there are big earthquakes. They are not the first. Actually, the first are smaller, and you have the biggest that are actually come a bit later, you see, because first they are just propagating. And then what I think is really cool here is that the dike stops. First of all, here you don't have anything. You know, you have this kind of...
It's like an elephant.
Huh?
The figure is like an elephant.
An elephant.
Has a trunk and
Yeah,
body.
it's true.
Yeah,
It's true. So you have basically after the trunk you have nothing, right? So you can see the trunk. And then you see where the head is of the elephant, the dike stops because you see it doesn't go any farther. But actually what happens after that? It happens that the seismicity decides to actually go back a bit and you have a lot of earthquakes here in this area, even relatively large like this and this, and you have almost nothing in this area, even if the dike actually reached this distance. So this is quite cool. And I have my own explanation that I'm going to tell you. Is like it's an explanation that occurred to me after he was born. Because I have this analogy of when a baby is born. So when a baby is born, you have the first big thing that you have is the head of the baby, right? And then this makes a lot of pain. And, and this is this pain, you know, like basically the dike, if you sit, yeah, you create, this is the pain, you know, but then basically this advances, and then you have, so if you are in a particular location, when the head is really arriving of the dike, then you have a lot of pain. Then you have the head, but then here you still have seismicity for a while. Why do you have still seismicity? Because the thickest part of the dike has not yet come. So you, after the head, you still have the shoulders of the baby, right? But then once the shoulders are gone, the pain is gone. So basically, maybe, yeah, maybe, but it makes sense also in a Coulomb stress way that you have like really like a crack shape. And a lot of the stress is really between the time you have the tip and the thickest portion of the dike. And then after that, here you are in an area where there is no stress anymore. So you have no reason to actually have the earthquakes. And what happens here? Here, probably what I think it happens is that the dike is propagating and the magma is flowing. And then you have the shape of the dike, but then once it is arrested, the flow within the dike stops. And this also creates a difference in pressure within the dike, because you know the flow is creates a gradient by itself because you have the flow. Once the dike stops, then the flow goes back because you create basically just a part of the pressure within the dike is just due to the flow of the dike, of the magma within the dike. Once you stop this, you create a different distribution of stress within the dike, and these different distributions of stress creates the fact that you have some flow going to the back of the dike. At least this is what I think happens, but I'm not sure. This is just my interpretation of why suddenly you start to have earthquakes at the bottom.
So how do you know the time evolution? It starts there and it's going that way.
How do you know?
The time. I mean,
So, like time,
what if it starts somewhere and it's propagated this way? How do you know it starts at the system?
here, so here is the magma chamber. This is the magma chamber. This is distance from AVC is basically the volcanic complex where the magma chamber is. Okay, so here the distance is 0, means the magma chamber is here. This is time. So everything starts at the magma chambers, and time is going, and it goes distant, distant, distant with time. Then at some point it doesn't go any more distance, it just stops. You see, there is no seismicity farther there. It stops. But then the seismicity actually goes back, you see, a little bit.
Yeah, I see.
Yeah. Okay, anyway, so this is also seen. This pattern is not the same, it's different. But you see similar patterns also when they do industrial fluid injection. So for example, if you fracking, you know, and geothermal energy, they inject fluids at high pressure, and then you see that the fluids spread or they create a crack, depends on the rheology of the rock. You can either create a real hydrofracture, and then it's really similar to a dike, or it goes more in the pores. So dikes are not so leaky, you know, they don't leak the fluid. It's really like a fracture full of magma. Industrially, generally you have something in between. You have a crack, but you also, the crack leaks some fluid in the pores. So you have the two processes together. It's like two end members, pore transport in the pores, transport by a crack. You are somewhere in the middle in industrial things. And you see it's not the same, you see something different, but you also see that seismicity advances and spreads, and you see maybe a different curve. So if it is really like a pore transport, pure, you see something that goes like a square root of time, because it needs to, you know, it's like a diffusion. You have a pressure and then it diffuses. Exactly, and this goes as like a square root of time. While here is more like an exponential thing, so it's probably something that is more like the pressure of the magma chamber, pressure within the magma chamber is very high at the beginning and feeds the dike, but then while the dike is being fed, we have a drop in pressure. And then this creates like an exponential decrease in the velocity, because the pressure at the inlet is decreasing. Basically, you have a conservation of mass. Some mass goes away, so it means that the pressure drops. And while you have this pressure drops, also it slows down.
Pressure difference.
Yeah. The pressure difference commands the flow. Yes, exactly. So in industrial activities, generally they can keep pressure relatively constant at the inlet. Is generally it's like they sustain pressure. So you have a different pattern, but you can actually observe your own, check your boundary conditions and take similar models. You know, just check: do I have constant flow? Do I have a constant pressure at the inlet? How everything is developing. Do I have porous flow? Do I have a crack? Do I have a mix of the two? There are all these models. They are for the industrial applications. They are also there. And then the data are also interesting because you can see a lot of details because they have very good monitoring sometimes. And what actually dikes have that industrial applications don't have is that they are so massive. You know, sometimes dikes are like 1 cubic kilometer, but it takes time to inject 1 cubic kilometer of water, right? So you have bigger earthquakes. You have bigger earthquakes. You have also these patterns are very. I mean, here there was a very good monitoring, considering that it is in a desert area. But when these things occur in areas that are well monitored, you can also have very good data, like in the Cambridge.
Why we need to inject water in the dikes?
No, I was comparing, sorry, it was confusing. I was comparing a magma chamber injecting magma into rock with an industrial activity where people inject water in rock.
Why they inject water into the rock?
Industrial activities for different reasons, generally for geothermal energy. So basically people inject water to create fractures, and then they create a circle, they put a well here and a well here, they create two wells. One well, they pressurize and they create fractures in the depth. Depends, they calculate the depth that they want, depends on the pressure, temperature difference that you want to achieve, and a lot of considerations. They inject high pressure, they crack, and then they create a circle by which you inject cold water, it heats up by flowing in the fracture network and comes up as a hotter water or steam, and then you go and you do a circle like this. Iceland is full with these things. There are geothermal power plants where you can really see this.
I visited one.
You visited one, yes. True. Yeah, and they explain to you, and then you ask the question, so what about induced earthquakes? This is an induced earthquake. Earthquakes that are induced actually by the pore pressure that you induce by these operations. Or maybe it rains and then you have more pressure, or maybe you have a drought and then, or not so much rain for a long time, and then you change all the pressure, you know, of the fluids. And so this is even one possible job that seismologists get, you know, to work in kind of infrastructures because they need this kind of work to understand what they cause, because people may complain. There have been cases with people complaining a lot, like in Switzerland there was a very famous case. It occurred in 1999. They started these operations. They said, okay, if actually they did it in an active area, that is maybe not so wise to start with, but some countries have only active areas, so what are they going to do, you know? And then they said, okay, if we get a magnitude 3, we stop. So they started to inject, and then earthquakes came, and they took off actually. Magnitude 3 was reached, then they panicked also a bit, they shut down the operation. They changed the pressure from very high to basically 0, and even started to extract fluid to go back, which is when a 3.4 occurred. Exactly when they were extracting the water, or after extraction of some water, a 3.4 occurred. And this 3.4 was felt by the population. It was Switzerland, so you know it's rich people with nice houses that complain a lot by culture. So this created billions of damage, even if it was tiny cracks, but you know, expensive houses, and close to a town, Basel. So they had to basically close it down, and they, you know, it was like a huge investment that actually brought nothing, brought only big expenses because of this. So then a lot of questions were raised. And what should you do to actually control the magnitude? Controlling the magnitude is difficult because magnitude is basically controlled by the biggest magnitude that you're going to get is actually a stochastic process. You can never control it really fully, but let's say it's depending on seismicity rate and depends also on the B value. If you change the B value, you may have a big earthquake even if you don't change the seismicity rate very much. So you have to, it's a delicate thing. And people started to look at these processes a lot. Okay, what if the extraction actually caused the biggest magnitude? What if, actually I don't think now they do, they actually go slow. They try not to change their stress very much. They try to inject slower, and if something happens, go slow in their, you know, not just drastically change your stress conditions, because this may bring changes that you don't actually want. But this is, so actually models to figure out exactly the magnitude of the earthquakes to be produced are very, very, you know, state of the art and even not very well understood. These are open questions. How do I control the magnitude of my operation? Now after many cases, they decided to go by this slow down rather than actually change abruptly. But it's also not my topic, so I'm not going to develop so much.
How the earthquake could generate it in these cracks caused by the water?
So actually the biggest earthquakes are not those that are induced just by the cracks or created by the cracks. These are generally not big. The big earthquakes generally are because you have a fault that is there already, and you are increasing the pore pressure in the fault plane, and so you are unlocking the fault, and then you have stored the stress that was there already. But actually this is how you explain a magnitude 6. Probably a magnitude 3 is fully in the possibilities of just pressure induced by the cracks. Okay, so induced seismicity goes probably like fracking has relatively by itself, by creating the fractures, relatively small ones, like 2 or 3 already is, I think it's quite big. I mean, you need to have some pre-existing seismicity and structures to have this kind of seismicity. Then actually induced seismicity can be bigger than that. It can be 4, 5, or even 6, very rarely. But then generally it's really like more, some people make the distinction between induced and triggered. So the induced is when you really are providing the entire stress or energy to actually create an earthquake from nothing, and triggered is more, you have something there already sitting there tectonically, and you are just making a clock advance on something that would have happened maybe in 100 years. You are providing some,
Accelerating the process.
yeah, you are providing some energy that really makes it happen now. Some people distinguish between these two. It's not always very easy. So one method to distinguish would be to actually know this, so like use these models very well and calculating really your probability of having earthquakes given a very precise stress change, but you need to really know your business quite well, because you need to know how the fluids are propagating. Are they infiltrating a pre-existing fault? Are they just moving in the porous medium? Are they creating a crack? What are they actually doing? How much pre-existing seismicity is there? So I actually need to monitor the area even before I do my operations, because I don't want to change my network only just after that. Otherwise I cannot compare. So basically I install my network before I monitor. In this way I can check whether there is any active area already or area with some seismicity, calculate my rates, and then start to do my operations. I mean, this is even safer for the industry, because they can, you know, they can assess better what is the likelihood of something to happen, and be less liable for later if something should happen, because they were careful and they assessed the risk in a careful way. Some countries need the energy, right? Every country needs the energy, so you need no energy collection method is entirely clean. Either you burn the coal, or you do nuclear stuff, or you do geothermal, which is relatively clean, but then it has also these side effects. So you need always to know your hazards or risks and calculate. Yeah.
When we construct dam and when water is flooding up, sometimes it does induce or trigger earthquakes. There are earthquakes when there is
Yes,
dam.
can be both, like when you have a dam and you are filling up. Also, I think in Iceland it occurred a lot. You are seismicity, can be close by, can be even be far away. And sometimes you see that there is a paper, I need to dig it out. There is a paper that shows in Iceland that when the level of the dam was raising, with the same trend, the seismicity at a distance of, I don't know, with a delay of a couple of months, seismicity at a distance was raising exactly with the same trend as the water. Because you are increasing the pressure. Yeah, you're increasing the pore pressure by doing this, especially in a country that has a lot of fluids in the upper layers. Sometimes seasonally you see, you know, like snow load, and the snow load goes away, you can actually see.
Even if the fault is inside the dam, under the dam, water may get in and create
Yes,
problem.
it depends on the permeability, right? So if you have a fault, actually they try to look even, now it's again not my topic, but I will try. I saw that sometimes they create a dam, you know, they fill it up, and then it depends where your faults are. Because, for example, if you have, imagine that you have a normal fault here.
So,
Is this fault going to be favored or locked by the dam filling?
it will be favored, I think it's higher down, because
We are adding weight.
load. So
It
will
will actually go locked, more locked, but then you need to be careful when if you are emptying the dam very quickly, right? You know, it goes in both ways, right? And the same is, or the opposite is, if you have actually, well, actually generally it's, if you have a truss fault, again, no, actually, this was sorry, I said wrong. So this becomes locked,
Yeah.
you know,
That's
because the water wants the fault to push down, and the movement wants to go up. While here the fault wants to actually go this way, and water helps. So, yeah, in the first situation, you are going to likely trigger an earthquake actually by filling the dam. In the other case, you are going to stabilize the fault. But then it may be dangerous in the opposite way. So you have to consider. And then there are countries, as you know better than me, that have also rain seasons. And then you can fill it up really very, very, very quickly when you have the monsoons or something. And then or you have countries where you have droughts, and then you actually drain these lakes for years and years and years. And then you may, like there are a lot of studies in California with the season and the drought seasons and El Nino, whatever, that shows that there are correlations between water level and seismicity in California, for example. Very, very interesting papers that show this link between fluids and seismicity rates. Yeah, and so in general there are interesting associations between these, particular physics and also in volcanoes, because in volcanoes you often have the same conditions. You have fluids traveling in the volcano. So I mean, even if one person is not particularly directly interested in volcanoes, it has like having a look at the phenomena observed are going to help in dealing with seismicity in geothermal areas, for example. They are actually similar. There are similar features. Okay, maybe a last thing. Okay, this is just another kind of curiosity. So this again is the Japanese dike. And just, what you can do if you have a good data set and you are a good student. This was a student I gave her the data set, she was super good. And after 20 years, people had seen these data sets and worked at it and so on, and she saw something that nobody had seen. So one can, if you squeeze your mind and you have nice data and you go deep, you can really discover cool things. So this was the seismicity, the gray dots. We discussed this already. We had this, the dike propagating, hitting the islands, and the fault, stopping. Actually, you see here also this pattern of seismicity going back. Straight after the dike hits the fault, the thickness of the dike probably got bigger in the back for a while. And then here you have these lines are the largest earthquakes. 5.6, 6.2. This one is probably the one that just stopped the dike. 5.7, 5.4, 5.9, 6.1, and so on. There are some, she recognized that there are a lot of seismicity, like lines that are not associated to a big earthquake. For example, here was not particularly big. Also, this one was not particularly big. Here there was something, and here, but actually not the biggest earthquakes. There were these stripes of seismicity that sometimes were not associated to a big earthquake. And then she looked at this. And she found, look at this one for example, that if you plot, a very, very cool thing to do is to plot the migration. We discussed this already. If you have some seismicity and you see that it occurs in a volcanic area, geothermal, whatever, even maybe tectonic, but in tectonic areas you generally don't see these migrations. But sometimes in volcanoes you see. So you plot, what do? You plot the distance from a given point, from the earthquakes in time to a given point where everything starts. So you locate the point where everything starts, and then you have your axis, x-axis with the time, and then you have your y-axis with a distance. It can be 3D distance, it can be just distance in the volume, or it can be in map view. It depends on what you want to do. Then you plot it, and you see this migration. And also again here you see that the migration also had something like a hole in the middle, but not everywhere. Like here you don't see this, here you kind of see it. And then the migration has a velocity. Okay, so you check this velocity. The velocity is already informative of the possibilities of processes that you have. So velocities may be, like here in this case was 1 kilometer a day. We talked about the velocity of dikes by themselves. Is more like when they are very deep, they can be very, very slow. But if they are shallow, generally they are like 1 kilometer an hour. Okay, for example. Here was more 1 kilometer a day. Then there are migrations, like these porous flow migrations, square root of time. They go actually 0.1 kilometer a day. They go like, or even less. And then here you have 1 kilometer a day. When you have 1 kilometer a day, I mean, it's not that it's like it's just a rule of thumb, okay? But there are, it is a bit too quick for porous flow, and it is a bit too slow for actually really advection of fluids, like really fluids moving and propagating. And she checked what were the characteristics. So first of all, one could see basically that these were kind of complementary. So one could see this maybe was the number 1, then number 2 occurred at the tip of number 1. Number 3 occurred at the tip of number 1 and number 2. So it was filling up here. So you see this is like a slip which was basically filling up the, and then also this, they basically filled up, you know. They were all complementary, meaning that if you add them up, you end up having more or less a constant slip over the whole thing. So she checked that there was migration and there was this. And so basically, she actually did more than this. I didn't put so many figures. But basically, she also inverted the deformation at the GPS station that were available. And one could see that, so basically you have the dike, fattening, we discussed this. And then you have these GPS arrows moving away. And she checked whether this other seismicity that looked kind of above the dike, what that could be. So she tried to put on top of the dike opening, more opening. But this wasn't fitting very well the GPS data. She tried to put only, since there was a nice catalog with also focal mechanism, she tried to put all the focal mechanisms, so to model all these earthquakes as earthquakes. So dike, fattening, plus the seismicity as earthquakes, each individual fault, how it slipped, to check whether the deformation was well explained. It was better, but not enough. So in the end, the final explanation was that one needed to have 100% more fault slip than what you actually measured in earthquakes. Like more slip. So basically that there was this noise. È più giù l'audio. So basically that these actually are the signature of slow slip events. Have you talked about slow slip in the past? Slow slip events that occurred because you had basically the dike fattening, and then on the normal faults at the top, the dike was fattening, and then these normal faults were slipping partly as real earthquakes with, like high frequency earthquake, regular earthquakes, and partly as slow slip events. And these slow slip events were these migrating, 1 kilometer a day, so really slow, you cannot really measure, but then, okay, so basically you have a slow slip, but then the fault is you have a lot of patches that are actually asperities, and they will break really high frequency, and those are all the points. So the points are really like earthquakes that break but are occurring on a fault that otherwise also slips slowly. and they go, and you see all these migrations. And this you may see also in, so there is evidence also in industrial operations about these slow slips that you may find in some areas. Yeah. Okay. Maybe we can finish here. Okay, only the last thing. This is again an Icelandic thing. I wanted to just show you that sometimes you have weird migrations, so like what occurred in this case actually is not really visible. Here. I will talk about it later because I'm not sure about the paper where it was taken and I don't want to get confused. No, but I think it is like, this is a case where actually the migration occurred from the top to the bottom. So you expect if something is ascending that you migrate from here and then you see things ascending. How would you interpret if you have first a cluster here, then a cluster here, then a cluster here, and then a cluster here? What would you, I can tell you later what they interpreted here. It was a bit of a weird case. Also, you see it's also quite deep. You see a lot of clusters all the way down to the moor and below. This is in Iceland again. And you see an eruption started already in the very early time. So the first cluster is actually a dike reaching the surface and erupting. And then if you go ahead in days, you started to see that seismicity activates at lower levels. And this actually follows sometimes where you have some more eruptive bursts. So what they interpreted here was that actually the eruption topped. So basically you decrease the pressure in the upper source, and then you had a difference with a lower source, and then the source activated because you had like empty here, and then creating a pressure gradient with a lower source. And then, okay, this was then becoming active, almost sending magma, and then you had a burst in the eruption. And then when this one was also empty, then the one below, and then again the one below. So like a subsequential, so this is the figure that they made. Like first, you have the eruption, and then this is empty, and then basically you have the effect of this being felt here, sending magma up and feeding the eruption, and then this effect being felt here, sending magma up, and so on. So sometimes this could be also a process where you have a lot of levels communicating, and maybe weird, you know, sometimes to see a migration that goes down and you think what happens, but sometimes it's just a pressure. You don't have really anything migrating from the top to the bottom. You have creating a pressure gradient, yeah, by emptying the upper chambers. Okay, see you, let's have a break and see you in half an hour.